Hey guys, welcome back to the Blimp video channel. My name is Craig Enders and I appreciate you tuning in. In this video, I'm going to talk about Blimp's modeling framework. I describe something called a factored regression specification and explain how Blimp leverages that to provide some unique modeling possibilities. Finally, I show how to specify factored regressions using Blimp's simple scripting language. Before we get started, I want to acknowledge the Institute of Educational Sciences for their support and point you to the project's website. You can download Blimp at the same homepage. To provide a context, let's look at a multiple regression model with three predictors, x1 through x3, any one of which could be missing. In the path diagram, straight arrows denote regression coefficients, and curved arrows reflect associations among the predictors. Blimp allows for a variety of different variable types. Outcomes can be normal, skewed and continuous, latent variables with multiple indicators, binary, ordinal, multi-categorical nominal variables, and even count variables. These variable types are available for both single-level and multi-level regression models with up to 3 levels. When we analyze complete data sets, we usually don't make assumptions about the predictors. However, incomplete regressors require a model that describes the distribution of their missing scores. Blimp imputes the missing values by sampling plausible replacement scores from those distributions. Blimp also allows predictors to have different metrics, but the variable types and associations among the regressors dictate the optimal model specification. I previously mentioned that Blimp's computational engine is based on something called factored regression. The idea behind this strategy is to express the multivariate distribution of our variables as a collection of simpler models and distributions tailored toward data and analysis. In this way, we can avoid making assumptions about the multivariate distribution that might introduce bias. As a simple illustration, let's think about bivariate normal data with x and y as the variables. The graph on the left is the familiar bivariate normal curve. I generically reference that distribution using function notation with x and y inside parentheses. The terms on the right of the equal signs say that the bivariate distribution can be expressed as the product of two simpler distributions, one for the outcome and one for the predictors. The middle panel is a regression where y is predicted by x, and the normal curves are the conditional distributions of y at 3 different values of the predictor. The symbolic notation has y given x inside the function. Finally, the rightmost panel is a univariate normal distribution for x stemming from an empty regression model. The symbolic notation is just f of x. The factored regression specification works with the models on the right side of the equal sign, and it ignores the multivariate distribution on the left. Factored regressions aren't necessary with multivariate normal data because we have good missing data handling methods for that context. As a more compelling example, consider a model with a binary predictor and a continuous outcome. We no longer have an off-the-shelf multivariate distribution that describes the co-occurrence of a continuous and binary variable. However, we can still express this unknown multivariate function on the left as the product of the two simpler univariate distributions on the right. The middle panel is a regression where y is predicted by x, and the normal curves are again the conditional distributions of y at each level of x. Finally, the rightmost panel depicts the discrete distribution of x stemming from an empty logistic or probit regression model. Beyond models with discrete and continuous variables, there are many other applications where we might want to adopt a factored regression specification. Examples include models with interaction effects, polynomial terms, and random coefficients, among others. As an example, factored regression is ideally suited for moderated regression models with incomplete interaction effects. Blimp accommodates a variety of interaction effects, including interactions involving pairs of manifest variables, pairs of latent variables, and even pairs of manifest and latent variables. Now that we have some vague intuition about factored regression specifications, I want to show you how to implement these models in the Blimp scripting language. Returning to the multiple regression model, let's look at Blimp's default specification for predictor variables. The factored regression consists of a univariate model for the outcome variable and a multivariate distribution for the predictors. In my symbolic notational scheme, the multivariate distribution on the left has all 4 variables inside the function. Again, we don't need to make any assumptions about the shape of that distribution. Instead, we work with the 2 simpler distributions on the right. The first term is the univariate distribution corresponding to the focal regression model, and the second term is a multivariate normal distribution for the predictors. The path diagram shows that the factorization is splitting the model into 2 parts, one for the outcome and one for the predictors. The code on the left side of the screen shows how to specify the model using the model command. Following the model line, we simply express the path diagram using a single line of code. The tilde is like an equal sign in a regression equation with the outcome variable to the left and the predictors to the right. So all we need to do is specify the dependent variables model, and Blimp figures out how to set up the predictor models. The default specification is actually very flexible because it handles normal, binary, ordinal, and multi-categorical predictors. Blimp uses a latent response variable framework to integrate categorical variables. For example, a binary variable imagines a normally distributed latent variable with a single threshold cut point that divides the continuous distribution into two segments. Ordinal variables are similar, but they require multiple threshold parameters that divide the distribution into multiple discrete segments. Finally, multi-categorical nominal variables use latent difference scores that are essentially continuous versions of dummy variables. Let me show you what this looks like with x3 as a binary predictor. The model line doesn't change, and we still have y predicted by x1, x2, and x3. I now use the ordinal command to define x3 as a categorical variable. Variables listed on the ordinal line can either be binary or ordered categorical. The nominal command works in the same way. Looking at the path diagram, the circle represents the underlying latent response variable, and it is that latent response variable that links to or correlates with the other predictors. A link function converts the latent response variable to discrete categories, and it is the resulting dummy code that predicts the outcome. The examples thus far have assumed that all predictors have missing values. However, complete predictors don't require a model because there are no missing values to impute. In most cases, it's a good idea to simplify estimation by telling Blimp not to estimate a model for these variables. Looking at the code on the left, you do this by listing complete variables after the fixed command. Looking at the path diagram, you'll notice that x2 doesn't have a residual arrow pointing to it, which indicates that it doesn't require distribution. However, x2 still conveys information to the other predictors via straight arrows connecting it to x1 and x3. Finally, the symbolic notation similarly says that x1 and x3 follow a bivariate normal distribution that conditions on the x2 variable to the right of the vertical pipe. Blimp's default specification is very flexible and convenient because most of it happens behind the scenes. However, there are some situations where we might want to be more specific about our predictor variables. For example, we may want to model nonlinear associations among predictors or specify metrics other than normal, binary, ordinal, and nominal. To do this, we need to set up the model a bit differently and use something called a sequential specification. The sequential specification replaces the multivariate distribution for the predictors with a sequence of univariate models and distributions. Essentially, each predictor becomes a dependent variable in its own regression equation, and we use a path model to represent the associations among the predictors. x2 is complete and never appears as the dependent variable in a regression. Looking at the code on the left, the model command now specifies three regression equations. x3 is predicted by x2, x1 is predicted by x3 and x2, and y is regressed on all three explanatory variables. The sequential specification allows for nonlinear associations among the predictors, but it also accommodates skewed continuous variables, latent variables, and even count predictors. Blimp's computational engine uses the Bayesian framework and Markov chain Monte Carlo, or MCMC, algorithms. Broadly speaking, MCMC consists of two steps. First, Blimp estimates a series of regression models using the filled-in data. Next, it uses the resulting model parameters to construct distributions of missing values from which it samples updated imputations. The diagram on the right illustrates a simple imputation scheme for the outcome variable. The normal curves are the distributions of missing values at three levels of x, and the black dots represent predicted scores. The white circles represent plausible imputations, which I jitter off vertical lines to enhance visibility. Blimp samples imputations from these distributions. For example, at the lowest value of the predictor, the orange dot represents an imputed score drawn at random from the distribution of plausible replacements. A similar process applies to the missing outcome scores at moderate and high values of the predictor. Repeating this process for each missing observation produces a filled-in data set like the one shown in the figure. The iterative process is repeated for many thousands of cycles, producing parameter estimates that effectively average over many possible realizations of the missing data. That concludes the brief tour of the Blimp modeling framework. The next videos in the series dig a little deeper into the Blimp scripting language and illustrate how to interpret the results of a Blimp analysis. Thanks again for tuning in, and I hope you check out future videos.